Hey everyone, and welcome back to our study of chemistry here. Today we're finally looking at chemical reactions. So the big important thing here is to figure out when a chemical reaction has occurred and kind of separate that from some of the stuff we've been talking about recently before, because we've been looking at some things that are physical changes, not chemical changes. So a chemical reaction involves a change in the bonding partners. So instead of being bonded to the same atoms I was before, I'm going to find new atoms to bond to. And that's a key difference between a chemical reaction and a physical change. Atoms will break their covalent bonds to each other and form bonds with new partners. Okay? Ions often change the number of electrons that are on them during the process. So, like if you look at the formation of sodium chloride, um, that formation process generally involves an exchange of electrons. We're actually going to be studying a reaction between copper nitrate and silver nitrate and copper that forms copper nitrate and silver. Is one of the things we're going to be studying. That's our SL Nova study this year. So the really important piece to understand is that the reactions produce materials with new properties. Okay, just like when we were talking about molecules compared to atoms, there were new properties that existed within the molecules. As we do a chemical reaction, we're going to create materials with new properties. All right, so here we have water freezing. This is something we've been talking about for a bit now. Obviously, when I make water cold enough, it begins to change state from a solid liquid to a solid in this case, which is freezing. Um, Water is staying water here. That is the key to a phase change, right? If I melt this, I will get water back. That is a very important and identifying factor. Whereas in this video, I am pouring sheep's blood into H2O2, and hey, look what happens. So what's the difference between those two videos? What were we seeing that was a major difference? Okay, the key concept is that the physical change didn't alter the bonds. When we're watching ice melt, the ice is staying H2O. It's two hydrogens bonded to an oxygen. Okay? Whether it's steam, liquid water, or ice, water is two hydrogens bonded to an oxygen, dihydrogen monoxide. Okay? No matter which state it's in, it stays the same molecule. That's a physical change. A chemical change, however, is where some bonding partners are changing. And usually there's something that's going to be evident to us in these sorts of changes. You're going to have different properties, different colors. Um, you might see something appear. Obviously, when they were pouring the sheep's blood into the hydrogen peroxide there was this giant thing that came out. This huge foam gets produced from this particular reaction. Okay, but you could see more subtle changes. Not everything is super dramatic like that. You could see color changes. You can see all sorts of things. We're going to talk about all that here in a bit. Um, the key really to understand this is that a chemical reaction, the properties are going to be different. That's really what I want you to key in on. Okay. Now, even though the properties are going to be different, that law of conservation of matter still is in effect. So, law of conservation of matter is, again, stating that matter can't be created or destroyed. We can only change its forms. Okay. So we can change what atoms are bonded together. We can do those sorts of things, but you can't create something new. All reactions, all changes are going to ultimately follow this. It's a fundamental law of nature that ultimately the atoms are going to not be made or destroyed during any of the processes that we're going to talk about. Okay. Ultimately, this is talked about in terms of reactions as a balanced equation. Okay. Balancing an equation means making sure that the atoms on one side of the equation are equal to the atoms on the other side of the equation. Okay. So if we look at a chemical equation, this is kind of what we'd be balancing. These are very important. There's a lot of pieces here. So first off, you have a reactant side and you have a product side. And we often read the arrow as the word yields or creates or reacts to form, something like that. Yield is a good term for it. We have reactants. Those are the things that are going to react together. They're going to form products. In this case, my reactants are glucose and oxygen, and they react together to form carbon dioxide and water. Now notice that the molecules have subscripts. So if I'm looking at glucose, there are 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms inside a glucose molecule. Whereas oxygen has both a coefficient and a subscript. So the oxygen occurs as what's called a diatomic molecule. There's 2 oxygen atoms bonded together. Okay, that's the subscript 2. But there are 6 of those that are going to react with 1 glucose molecule. Coefficients we can change. Okay, that's when you're balancing an equation, you generally are changing the coefficients around to make it sure that the molecules all have the right number there, so that your atoms are the same on both sides, so you don't create or destroy matter accidentally. Okay, we call the whole thing, the whole molecular unit, like H2O or C6H12O6, the formula for the molecule or the polyatomic ion or whatever it is that we're looking at. Okay, so this particular slide shows some pretty important language. You're going to be seeing this in a Quizlet deck as well. Now, the way this usually shows up for you is we might look at a model like this and ask ourselves, does this properly conserve matter? So in this sort of a case, what you do is you count the number of atoms on both sides of the equation. So on this particular chemical equation here, I see that there is nitrogen on one side. There's 2 nitrogen atoms. On the other side with the ammonias, there are 2 nitrogen atoms still. On the reactant side of this, I have 3 hydrogen molecules that give me a total of 6 hydrogen atoms. On the product side, I see that ammonia has 3 hydrogen atoms each. There are 2 ammonia molecules, therefore there are 6 hydrogen atoms. Okay, so this one does properly conserve matter. Ultimately, you count all of the atoms of each type. You got to count them for each type, and you got to ask yourself, are they the same on both sides? If so, then a model is properly showing conservation of matter. If not, then there's an error with the model. Okay, it's missing a molecule or something along those lines. Okay, it wasn't properly drawn unless the atoms on the product side equal the atoms on the reactant side. It's got to equal the number and the type. So how do you know when a chemical reaction has occurred? There's going to be something that you can observe. Okay, let's take a look at a few reactions and see what happens and see if we can start seeing some of these signs of a chemical reaction. So in this particular reaction, we see a golden yellow precipitate form. You can see all those little sparkly, the way it catches the light. It's actually a very pretty reaction, I think. Not all precipitates look like that. Some precipitates form like this. So as we pour the 2 liquids together, this big clumpy matter falls out. And actually, as it continues to react, you notice how there's a bit of a color change occurring as it starts to darken. Other ones, like this one, show formation of a gas. You can start seeing bubbling and the gas starts coming out there. And then over time, as you add more heat, there's a color change to the gas and it ends up having a huge release of energy. This particular one creates precipitate again. It's actually going to be modeled in SL Nova by us. So a lot of the signs are things that we can actually see. Like, for instance, we saw color changes. Okay, color changing, very obvious that a reaction has occurred. Okay, precipitation, so a solid forming when I mix two liquids together, obvious sign that there was a chemical reaction that occurred. Gas formation, okay, start seeing bubbles rising up out of things, very obvious. Odor, you might smell something. Not very obvious in videos, but can be very obvious inside a chemistry lab. Temperature changes, especially with reactions that we're going to be concerned about really soon. You would always see a chemical temperature change because we're looking at exothermic and endothermic reactions for hot and cold packs that we're going to be building. Okay, but temperature changes are actually very common as far as giving off energy or taking in energy. And density changes, a little more subtle. You'd have to actually measure the mass and the volume of your products, and then you would probably see some sort of density difference if you divided the two, that there had been a change there. pH changes. We actually often use color indicators for pH changes. So we use another reaction to detect that a pH change has occurred. You can also use pH meters, are very common. So ultimately, we get data from reactions, okay? And that's usually how you're going to be analyzing stuff. So let's say I had a reaction here. I'm going to take some coconut oil, and I'm going to do a reaction called saponification. That's going to take that coconut oil, it's going to make it into soap, okay? Now, let's take some data from this. So I started out and I had coconut oil and I mixed it with lye, and that created soap and glycerol, okay? I wrote down here my masses. So I started out with 100 grams of coconut oil, 20 grams of lye, okay? My products in the end, I created 115 grams of soap and 5 grams of glycerol. Now, if you notice, 100 plus 20, that gives me 120 grams. 115 plus 5 grams gives me another 120 grams. So the products and the reactants, their masses remain constant. That's that law of conservation of matter showing up again. Okay, so I did not create or destroy any of the mass. It's all there. It's all accounted for. Odor-wise, the coconut oil smelled like coconut. Lye doesn't smell like anything. The coconut oil turned into a soap, and that still has that smell of coconut oil. Okay, and the glycerol is still odorless. Now look at the densities: 0.93, 2.13, 0.95, 1.26 grams per cubic centimeter. Okay, grams per cubic centimeter can sometimes be confusing to students because you see that cm cubed and you're not really sure. You think you will need to like cube something. It's a unit. It's showing you that each side is being measured in centimeters. Notice that all the densities are different. Density is one of those really useful properties because generally things have different densities. It's harder to measure. It's not really obvious to the eye. Like I look at this and I see coconut oil, right? It's liquid, and coconut oil turned into a soap is obviously a solid, right? Soap's a solid, that's a liquid. I can see the difference visually, right? But I can also measure it through things like density, and that's huge, okay? Solubility in water is another very useful property. Coconut oil is not soluble in water, the soap is, okay? So that's huge. That's a huge one. So if I suddenly become flammable, if I am soluble in water, if I changed my melting point. Look at all those melting point data. 27 degrees Celsius, 318, 48, 17.8. The melting points are all over the place. The properties of the matter change. That's the key. So if you're looking for a chemical change, you're looking for data that supports that properties, like is it flammable? Does it melt? When does it melt? Right? What temperature does it boil at? Is it soluble in water? What's the density? What's the color? What's the odor? All these things add up to give us evidence of chemical changes. So another way to look at this would be with the law of conservation of matter problem, okay? And the key to a law of conservation of matter problem is that you start with what you end with, okay? What you start with mass-wise is what you end with mass-wise, okay? We don't create or destroy it. And a lot of times these are just one-step algebraic equations. They're not very hard. So let's say that I've got a reaction here. I'm going to take water and I'm going to do some electrolysis on the water. Doing electrolysis on water, you use one of these apparatuses here. You just fill this up and you run like an electrical current through it basically, and that's going to break apart the water, and it's going to get caught into gases that are going to go up into those test tubes. Okay, it's pretty cool stuff. So let's add 19.45 grams of water, and I'm going to make 17.3 grams of oxygen. Okay, well, how much hydrogen do I make? So it's water getting broken apart into oxygen and hydrogen. Okay, mass is conserved. So if the mass that I started with is 19.45 grams, I have to end with that much mass too. Okay, 19.45 grams would equal 17.3 grams of oxygen plus some unknown hydrogen. I'm going to call it X. Okay, now I'm going to subtract 17.3 from both sides of the equation, and I'm left with 2.15 grams equals the mass of hydrogen gas formed. The mass of hydrogen gas formed would be 2.15 grams. All right. Some thoughts on this. Matter is conserved. Okay, you're going to see this in lots of ways. You might see it in a model. That's a really common problem. Okay, it's very common for you to encounter problems where you have a model and you're evaluating someone's model, or you're making your own model, but usually it's evaluating someone's model, and you got to make sure that the reactants and products have the same type and same number of atoms. Okay, we could also see it in tables. If we were go back to the coconut oil reaction, we would see the mass of the products and the mass of the reactants equal each other. Always, always, always. And we even have algebraic problems to find unknown masses that occur. So this is actually huge. Like, I've seen situations wherein you have a quiz or a test and like half the problems go back to does matter conserve? It's going to be huge, and it's going to be coming up a lot. You're going to see this a lot in the homework. You're going to see this a lot in the quizzes, and you're going to ultimately see it on the cast. The properties of substances change. Melting point, boiling point, density, flammability, all of these things change when you do a chemical reaction. They're identifying properties. So if I'm trying to figure out if something is a specific chemical, I look at its properties and I ask, do all these properties line up? And if the properties line up, then that chemical is what I'm looking for. Okay, I can identify it by looking at the properties, looking at density, looking at flammability, looking at boiling point, melting point. There's a lab that I did in college called a qualitative analysis, where literally that's all you did is you just looked at all the properties of materials and you tried to identify unknown substances by asking yourself, are these true? Well, do these numbers and do these properties line up? Make sure that when you're looking at the properties, you understand what is an intrinsic property of a substance and what's the amount you got. because a lot of times there will be tricky problems where they'll give you like tables of data, and they're going to ask you like, are these, did a reaction occur? Are these the same chemical, right? And you might see masses or volumes. Masses and volumes tell you how much you have. Okay, um, they're not intrinsic properties. Okay, so water has a boiling point of 100 degrees Celsius. Okay, always and forever. It doesn't matter if I have a glass of water or if I have a swimming pool of water. If I raise it to 100 degrees Celsius, it boils. Okay, um, that's a property of water. If you bring it down to 0 degrees Celsius, it will freeze. It doesn't matter how much or how little you have. Okay, so don't be confused by amounts. That's just how much you got. Okay, look for properties like density, boiling point, uh, flammability, smell, these kinds of things. Those are intrinsic properties of a substance, not how much you have. All right, that's about it for today. Have a great night, and I'll talk to you guys later. Bye.